Welcome to another video from HEGARTYMATHS. It's Mr. Hegarty here, and we're continuing our integration videos. In this one we're going to talk about differential equations, and we're going to have two videos on this. This is the first one. So what I'd like to be able to do at the end of this video is to solve differential equations by separating variables and integrating. Okay, before we get going, what are differential equations? Well, a normal equation might be something of the form, I don't know, 2x add 1 is equal to 11. That would what you would call a linear equation, the equations we've been used to in the past. Now, a differential equation is an equation, it's got an equal sign, and it's got differentials in it, it's got some gradient functions in it. So this would be an example of a differential equation. dy by dx is equal to, I don't know, x cubed. That's a differential equation. Why? Well, it's an equation, it's got an equal sign, and it's got x's and dy by dx's. So that's a differential equation. Something like this would be a differential equation. 2 dy by dx take away 3x is equal to 0. Again, these two would both be differential equations. And the reason they would be differential equations is that they have x's, numbers, operations, and dy by dx's. Now, there are various types of differential equations out there: first order differential equations, second order differential equations, etc. The ones we're dealing with in this video only have a dy by dx in them. They don't have, let's say, a second differential in it, like, for example, d2y by dx squared would equal, I don't know, 6x. They're not of that form. They don't have a second differential in them. The ones we're dealing with in this video simply have one differential in them. So that's what a differential equation is. Now, the aim of the game, to solve a differential equation, what you want at the end of it, you want y as the subject of the formula, and you want it with some function of x. And because you will have to integrate to get a y from dy by dx, you will have a constant of integration as well. So that is the aim of the game, to go from the differential equation to something like that, where y is the subject of the formula, it's a function of x, and you've got a constant of integration. So that's our aim. Now, I just want to show you that actually we have actually solved some differential equations in the past. So here's some examples. Let's just do quick examples. Dy by dx, if I told you dy by dx was equal to x cubed plus 4, would you be able to tell me what y is? Well, you would. Y would be a quarter x to the power of 4 plus 4x plus a constant of integration. So what you've done is you've integrated both sides with respect to x. And having done that, dy by dx, once you integrate that, you get y back. Once you integrate x cubed plus 4, you get a quarter x cubed plus 4x plus the constant of integration. So we know how to solve differential equations of the form dy by dx is equal to some function of x. Okay, what we do is we integrate both sides. On this side we get y, and on this side we work out the integral of this, and we add a constant on top of it. Now, if I just complicated things ever so slightly further, but hardly at all, if I said something like x cubed subtract 4 dy by dx is equal to x to the power of 5, let's say, and I asked you to deal with that, well, the first thing I would do if I was you is I would rearrange to make dy by dx the subject. So I would say x cubed subtract x to the power of 5 is equal to 4 dy by dx. And then what I do is I divide everything by 4, so I'd have a quarter x cubed take away a quarter x to the power of 5 is equal to dy by dx. And then what I do is to solve, I'd integrate both sides with respect to x, and I would get that y is therefore equal to a 16th x to the power of 4 subtract a 24th x to the power of 6 plus a constant of integration. So I can solve some differential equations already. Ones where I've got a dy by dx, basically ones where I've got a dy by dx is equal to some function of x, or that I can adjust it so it is equal to some function of x. All I do is I integrate both sides. Okay? this particular video, we want to go one step further and we want to deal with differential equations of this form. We want to deal with differential equations that are of the form dy by dx is some function of x and some different function of y. These are the type we want to solve in this process. And at the end, we want our answer to be y is equal to other function, which I'll call h of x at the end plus constant. That's what we want to get to. And there's a method to do this. So step one would be to get the differential equation in this type of form, so that the dy by dx is some function of x multiplied by some function of y. So get into star form, I'll call it star form, if it's not already in star form. The next thing that you would do is you would separate variables. You would separate variables and integrate. Now, what I mean by this is you would bring everything involving x to one side, everything involving y to the other side, and integrate both sides. So what I do is everything with regard to x, I want the dx on top, so I will keep the f of x here and have the dx here, and I will divide both sides by g of y, so I'll have 1 over g of y dy, and I will integrate both sides. Now, the left-hand side I'm integrating with respect to y, that's what this dy means, and the right-hand side I integrate with respect to x, that's what that dx means, and I get plus constant. Then I solve this thing, and lastly, if need be, I make y the subject of the form, or y subject. Okay? Now, to recap the process, what we're kind of doing, an easy way to think of it, we're treating the dy by dx as some sort of fraction. We're making sure the dx comes up on top, so it's not on the bottom anymore. We're keeping the dy on the other side. Okay, and what we're then doing is we're keeping everything with x, with the dx, and we're keeping everything with y, so the g of y with the y, so you'd have to divide both sides by g of y, and then we can integrate this side with respect to y, integrate this side with respect to x, and then I would get some function of y is equal to some function of x plus c. I can then rearrange and make y the subject of the formula. So y is going to be some function of h plus a constant. Now, it's important that you realise this in this form here, when you get an answer like this, this is called the general solution. And the reason it's a general solution is that c can be infinitely many answers. C is any constant. When you differentiate it, it will disappear. So it's because you've got c not defined. So a general solution is where c is any constant. Now, there will be times where they give you what's called boundary conditions. They will give you boundary conditions. And what I mean by these is they will give you a particular value of x and a particular value of y that are true on this particular curve, and you can substitute them in, so you can substitute values of x and y to get c. And when you do that and you write down that c and then you rewrite this with c defined, that then is got a different name, and that is called a particular solution. So that's called the particular solution. Okay, it's particular to the boundary conditions of that problem. Okay, so let's give this a go then. Let's start off with some examples. Let's find the general solution, so not finding c, just with the plus c of the following. Leave your answers in the form y is equal to f of x. Straight away, I'm going to write dy by dx is equal to 2 e to the power of x e to the power of negative y. I needed to break this up so it was a function of x multiplied by a function of y. Remember, we want our differential equations in this form, f of x, g of y. Now my f of x can be this thing here, and my g of y can be this thing here. Now I'm going to keep everything with y's on the left hand side, everything with x's on the right hand side, and rewrite this. So I'll have 1 divided by e to the negative y dy is equal to 2e to the x dx, and I'm going to integrate both sides, and I'm going to add my constant of integration. Now 1 over e to the negative y is just e to the y, so this is e to the y dy. We haven't integrated yet, and I'm going to take the 2 out. It's the integral of 2e to the x dx plus constant. Now we can do the integration. The integral of e to the y is e to the y. This thing here integrates to 2e to the x and keep your plus constant. Now I can take logarithms of everything. If I take logarithms of both sides, I'll get the y is equal to the natural logarithm of 2e to the power of x plus your constant. And that is in the form y is equal to f of x, and we're done. Okay, let's have a go at part B. It's already in the form dy by dx is equal to g of x, f of x, g of y. Sorry, f of x, g of y. It's already in the form f of x, g of y, where f of x is equal to tan x and g of y is equal to y. So we're going to separate variables and integrate. So what I'm going to do here, I'm going to write dy by dx is equal to, I'm going to rewrite it as tan x, like that y. I'm going to divide everything by y and multiply by dy by dx. So 1 over y dy is equal to tan x dx. And I'm going to integrate both sides, and when I do that, I get a constant of integration. Now the integral of 1 over y is the natural logarithm of y, because when I differentiate logarithm y, I get 1 over y. So when I integrate 1 over y, I get natural logarithm y. And the integral of tan x. Now the integral of tan x is actually in your formula booklet. The integral of tan x is the natural logarithm of sec x. Okay, and you've got plus c. So this here, this answer is in your formula booklet. Okay, right, so we are very close now. We just have to make y the subject of the formula, take exponentials of everything. So I would get y is equal to e to the ln sec x plus c, which I can actually break into e to the ln sec x e to the c. E to the c I can call just another constant. I could call e to the c something like a different constant. So that's a e to the ln sec x. E to the ln sec x is just sec x. So that would be a sec x, like that. So y is equal to a sec x in this case. And I'm done. Right, so that was the sort of easy introduction, as it were. Here's a couple of harder questions. Find the general solution to the following differential equation. So I'm going to put it in the form, I can put it in the form dy by dx is equal to x over 1 plus x squared tan y, like that. And I can separate variables and integrate. So what I'm going to do is I'm going to separate variables and integrate. So 1 divided by tan y dy is going to be equal to x divided by 1 plus x squared with respect to x plus a constant of integration. Now 1 over tan y, that's the integral of cot y dy. And this thing here, now you've got an algebraic fraction. The first thing you should ask yourself is the top the differential of the bottom? Okay, well, it nearly is, okay, because the differential of the bottom would be 2x. So I'm going to put a 2 there, I'm going to multiply by 2, and then I'm going to divide by the 2, so I haven't changed the original one. And now I'm going to have something that's a natural logarithm answer. Okay, now the integral of cot y, is in your formula booklet. It's one of the ones you can look up. And the integral of cot y is ln sine x. So this thing here, the integral of this is ln sine x. Okay, and this integral is in your formula booklet. It's in your formula booklet. Now this one is a straight log now. The top is the exact differential of the bottom, so it's a half the natural logarithm of 1 plus x squared, and then we have plus constant like that. Now, sorry, that would have been, not sine x there, just my mistake. That would be obviously a sine y. Now, That's the general solution. If I want to make y the subject of the formula, let's have a go at doing that. So what we're going to do is we're going to take exponentials of both sides. Okay, so taking exponentials of both sides, we'd have that sine y would be equal to e to the half ln 1 plus x squared plus c, which I can write as e to the half ln 1 plus x squared multiplied by e to the c, and I could call e to the c a different constant like a, so I could say this is a e to the half ln 1 plus x squared. Now what I could do then, that's sine y still, I could bring the power of a half up here using the log laws, so this would be sine y is equal to a e to the ln 1 plus x squared all to the half, and now e to the ln of that would just be 1 plus x squared to the half, so sine y would be equal to a 1 plus x squared to the power of a half. And if I wanted to make y the subject of the formula, y would therefore be arc sine or inverse sine, so arc sine a the square root of 1 plus x squared, like that. And I'm done. Right, the next one, find the particular solution. So this time we're going to find this constant that we've labelled in the previous one. We're actually going to find the constant, so we're finding the particular solution. So we're going to use x is 4 and y is 1 as the boundary conditions to do that of this thing here. So the first thing I'm going to do is separate variables and integrate. So I'm going to write 1 divided by y subtract 2 dy, bring everything with y on the left hand side. So that's the only thing with y. I want that on the left hand side now. Keep that dy on the left hand side, and then everything with x, this, and I'm just going to keep that there. It's not x or y, so I'm going to have is equal to negative 3 divided by 2x add 1 x add 2. Put the dx here as well. Remember there was a dx here, so bring that onto the right hand side and integrate both sides. So I'm going to integrate that and integrate that. Okay. Now I might have to do some separate working for this. I'm going to do working 1 here. So I'm going to call this working 1. Working 1. The integral of 1 over y subtract 2 dy. Well, that's an easy integral, you should know. That's the natural logarithm of modulus y subtract 2 plus constant. But we'll deal with the constant at the end. Now, working 2. This one's going to be harder, working 2. Now, this is an algebraic fraction. The top is not the differential of the bottom, and it looks like two distinct linear factors, so I'm going to try partial fractions. So for working 2, the first thing I'm going to do is I'm going to try and write negative 3 over 2x add 1, x add 2 in partial fractions, so in the form a over 2x add 1 plus b over x add 2. My next line, making this have a common denominator of 2x add 1, x add 2, I'm going to write negative 3 is equal to a x add 2 plus b 2x add 1. And then I'm going to do some substitutions. I'm going to let x be negative 2, and I'd get negative 3 is going to be equal to negative 3b, so b is equal to 1, that tells me. And then what would I let? I'd let x, well, why don't I just let x be 0 to avoid fractions? I'd have negative 3 is equal to 2a plus b. Now b is 1, so negative 3 is going to equal 2a add 1, so therefore negative 4 is going to equal 2a, so a is therefore going to equal negative 2. So I could rewrite this integral up here, the integral of negative 3 divided by 2x add 1, x add 2 with respect to x. I could write that as the integral of negative 2 over this plus 1 over that. So I'm going to rewrite that as 1 over x add 2 subtract 2 over 2x add 1 with respect to x. And now both of these are ones I can integrate. They're both logarithmic ones. This one here I can integrate as the natural logarithm of x add 2, and this one here I can integrate. The top is the exact differential of the bottom, so it's natural logarithm of 2x add 1. and I could combine these to the natural logarithm of x add 2 divided by 2x add 1 using my log laws. Okay, so now I've done all the hard work. Let's combine working 1 and working 2. So working 1 and working 2 give, well, they give me on the left hand side the natural logarithm of y subtract 2 is equal to this thing, the natural logarithm of x add 2 over 2x add 1, but don't forget my constant of integration, c. Now we were told when x is 1, y is 4. So this is important. When x is equal to 1, y is equal to 4. We can substitute that in here and get what c is. So let's do that. So we'd have the natural logarithm of 4 take away 2, which is 2, would be equal to the natural logarithm of 1 add 2, which is 3, over the natural logarithm of 2 add 1, which is 3, plus c. Now this is going to be 0 because that's natural logarithm 1, so c is going to equal ln 2. Okay, so what did it ask us for? It asked us to give our answer in the form y is equal to fx. So what we've got ln y take away 2 is equal to ln x add 2 over 2x add 1 plus ln 2. We could combine these lns, that would be the best thing to do here. Remember that ln a plus ln b is equal to ln a times b, so we could write this as ln 2x add 2 over 2x add 1, multiplying the 2 on top there, and therefore that's the natural logarithm of y take away 2. Taking exponentials of both sides, y take away 2 would therefore equal 2x add 2 over 2x add 1, and then adding 2 to both sides, y is equal to 2 plus 2x add 2 over 2x. Add 1, just like that. And we're done now for that question. So we have got it in the form y equals and it's a particular solution. And that's all I wanted to talk about for this video. To make sure you understand everything, make sure you do the following exercise. Thanks loads for watching.